This is Physics 2120, Lecture 11, and today we're going to talk about RC circuits. A direct current circuit can contain capacitors and resistors, and if it does, the current is going to change with time. When the circuit is completed, the capacitor starts to charge if it was in an uncharged state to begin with, and it continues to charge until it reaches its maximum charge, which is the capacitance times the voltage across it. Once the capacitor is fully charged, there can be no more current in that branch of the circuit, and so the current goes to zero. Now, as the plates of a capacitor are being charged, the potential difference across the capacitor increases. At the instant the switch is closed, the charge on the capacitor is zero, and once the maximum charge is reached, the current in the circuit is zero. The potential difference across the capacitor at that point will match that supplied by the battery, or whatever the electromotive force is in the circuit. So if I were to look at a simple RC circuit where I have a battery, a capacitor, and a resistor, and I have a switch, and I close the switch so that now I can get current to flow. I'm going to get current flowing around the circuit in this way as long as the capacitor is uncharged. And we see that what's really going on, the charge isn't flowing across the capacitor. One side of the charge of the capacitor is getting charged with one type of charge, and the other is getting charged with the other type. So what's really happening is electrons are moving around, and once we get enough electrons around that the battery can no longer push any more electrons, the current goes to zero. So if I were to look at the charge on that capacitor, it would be zero and would slowly increase until it gets to a point where it's not changing. And remember, current is the time rate of change of charge. So then the current is going to start out at a maximum value, and as I get more and more, it's going to be harder and harder and harder to put more charge in, and it eventually drops to zero. So what is the shape of these curves? That's what we want to figure out next. So let's look at my circuit. I have a switch. I'm going to close the switch. As I close the switch, I can start at the switch and I can look at Kirchhoff's rules for this. So as we come around from the switch, we go plus E across the battery, and then we hit the capacitor. There's going to be a voltage drop, and the voltage across it is whatever the instantaneous charge is on it divided by the capacitance, is Q equals CV. And I come around, and of course this is the direction the current is flowing, so I hit the resistor, I get a minus IR, and back to where we started. So this is the equation that we need to solve in order to understand charge as a function of time. Remember, current is dq dt. If we plug that in, first thing we want to do is we want to solve for I by itself. So if we were to take IR and put it on the other side, divide by R, we're going to get the current is E over R minus Q over RC. Get a common denominator, so it's QE minus CE minus Q over RC, and that's equal to I, which is dq dt. This is a differential equation that we need to solve. It's a very special type of differential equation. It is a separable differential equation. In other words, I can take this equation, put all the q's on one side of the equal and all the t's on the other side of the equal sign, and then I can integrate. So dq over q minus ce is equal to minus dt over rc. Now we can see all I have to do is integrate this, and I integrate this side from 0 to t, and then this side will be going from 0 to q, whatever q is, that is a function of t. So the first one's easy. It's just minus t over rc. The second one, we'll need to do a variable substitution. It looks like if we use y equals q minus ce, that work. So we're going to do that. Then dy is equal to dq. When q equals 0, y equals minus ce, and when q is equal to some function q sub t, y is equal to q minus ce. So we change our limits, we plug it in, we notice that we have a dy over y, and that's just a logarithmic answer. The natural log of q minus ce over minus ce is equal to minus t over rc. We need to solve this for q, so in order to do that, first we're going to take both sides raised to the power of e. And then we can do that and solve for q. Q is equal to CE times 1 minus e to the minus t over RC, or CE is the maximum value of the charge on the capacitor. And we're going to call RC, which has to have units of time in order for this exponential to work, we're going to call it by the variable tau. It's going to be something called the time constant. So, the charge on the capacitor varies with time, and it starts off at 0. T equals 0. E to the minus 0 is 1, so I get 0, and it increases exponentially to this maximum value, CE. Then, if we wanted to find the current as a function of time, we would take the derivative of this, and the derivative of 1 is 0. It's a constant, and so the integral of e to the minus t over RC, we get a minus 1 over RC out front. We plug that in, we're going to get an e over r. Now, this time constant represents the time required for the charge to increase from 0 to 63.2% of its maximum. This has to do with the way the logarithms work. And tau has units of time. Then the energy stored on the capacitor is also going to change in time. And remember, the energy stored on a capacitor is 1/2 Q times the voltage, or 1/2 CV squared. Now, the other thing I can do with a capacitor is once it's charged up, I can use it in a circuit that doesn't have a battery and have current to flow. In this case, when I start, if my capacitor is fully charged, it starts off at the maximum voltage, and then it's going to decrease, and it's also going to decrease exponentially. And the same thing with current. There's going to be the highest voltage across it, so the highest current across the resistor when it's closed, and then as the charge goes down, there's less and less voltage, so less and less current. So when a charged capacitor is placed in a circuit, it is discharged, where Q is the maximum Q times e to the minus t over RC, or minus t over tau again. And then the charge decreases exponentially. And at t equals 1 time constant, the charge decreases 63.2% of the way, so it's down to 36.8% of its maximum voltage in 1 time constant. And current is found in the same way. Current is some maximum current, and then it decays exponentially. So, let's look at a problem. An uncharged capacitor, C equals 5 microfarads, and a resistor, 8 times 10 to the 5th ohms. If E is equal to 12 volts, find the time constant of the circuit, the maximum charge on the capacitor, the maximum current in the circuit, and charge and current as functions of time. So, first thing we need to do is start out with the time constant. Tau is RC. That's pretty easy. We plug in those values, and we get the time constant for this particular circuit is 4 seconds. The maximum charge on the capacitor is C times the voltage of the battery. So CV, we multiply that and we get 60 microcoulombs. The maximum current is the voltage over the resistor. So before there's any charge on the capacitor, that's when I hit my maximum voltage. It's 12 volts over 8 times 10 to the 5th ohms. I get 15 microamps. So now that I have Imax and Qmax and tau, I can plug those into our equations and get charge as a function of time. We know charge as a function of time is Qmax, which is also CE, times 1 minus e to the minus t over tau. So we plug in our values, and we get Q as a function of time is 60 microcoulombs times 1 minus e to the minus t over 4. Current is very similar. I is equal to Imax e to the minus t over tau. So we plug that in. I is equal to 15 microamps times e to the minus t over 4. Notice that this is exactly dq dt. Now, before we go on with anything else, there's certain electrical devices you should know what they are and how they work. So I briefly wanted to talk about several of these. The first is a galvanometer. It's a main component in analog meters that are used to measure current and voltage. Now, most of the time we'll use digital meters that don't have a galvanometer anymore. It uses some circuits to analyze currents and resistance. But sometimes we need something that's non-digital. And the galvanometer essentially is just a coiled spring and a magnet, and as I move current through it, as we're going to find out in the next section on magnetism, I can create a magnetic field and I can get this needle to turn, and it's going to turn based on how much current or voltage is across a certain element. So it's a coil of wire mounted so it's free to rotate on a pivot in a magnetic field, and that field is provided by permanent magnets. And anytime I have currents going through a loop, I have a torque, which causes the coil to turn. The torque is always proportional to the current. The larger the current, the greater the torque. The greater the torque, the larger rotation of the coil before the spring resists enough to stop it. The deflection of a needle attached to the coil is proportional to the current, and once calibrated, you can use a galvanometer to measure either currents or voltages. An ammeter is a device that measures current. So a galvanometer can be used as an ammeter. Ammeters must be connected in series with the elements being measured because the current must pass directly through the ammeter. So in this case, if I wanted to know the current in the circuit, I would take my ammeter and connect it in series with the elements that I want to know what the current through them are. An ideal ammeter should have zero resistance, so the current being measured is not altered by the ammeter itself. A voltmeter is a device that measures a potential difference. And voltmeters have to be connected in parallel with the elements being measured. The voltage, remember, is always the same in elements connected in parallel. So in this case, if we wanted to find the voltage across R2, the voltmeter is connected in parallel with R2. And we have to understand that voltage has a polarity. It'll tell me which side is at a higher potential. Now, a voltmeter ideally should have infinite resistance. We don't want any current to pass through this branch. We want only the current to flow through here so we can measure the voltage across that element. Utility companies distribute electric power to individual homes by a pair of wires. And every house in the circuit is connected in parallel with those wires. One wire is always the live wire, and the other wire is a neutral wire that's connected to ground. So the potential of the neutral wire is always taken as 0. Now, in this case, actually, the current and voltage are alternating. We'll talk more about alternating currents later, but it's easiest to visualize if we think of our live wire at 120 volts and our neutral wire hooked to ground at 0 volts. So we'll have a meter here that's going to measure the amount of current that goes through here, and it'll measure the amount of energy that we're using. We have a main circuit breaker to turn this live wire off from the house. And we have individual circuit breakers that we can open and close to different circuits, and then across each circuit we'll have different resistances. Those can be toasters, hair dryers, washing machines, light bulbs, whatever it is that provides the load resistance. And so the current flows from the live wire through this back along the neutral wire. So that meter is connected in series with the live wire entering the house. It records your consumption of electricity. After the meter, it splits into multiple parallel circuits that you can distribute throughout the whole house, that each one has its own circuit breaker. Now, sometimes we have devices that require a higher voltage, or 240 volts. For example, an electric stove or a dryer have a lot of energy needs, and so there's actually a third wire that's maintained 120 volts below the neutral wire. So in that case, I hook up my dryer between the plus and minus 120 volt wires and get 220 volt potential difference between the two. Now, a short circuit occurs when almost zero resistance exists between 2 points of different potentials, and that results in an incredibly large current. In the household circuit, the circuit breaker opens the circuit in case of an accidental short circuit, and it prevents damage to either devices from heating up from so much current and causing a fire, or from a person being electrocuted. So a person that's in contact with ground can be electrocuted by touching the live wire. Now, electrical shock can result in many different things. It can resist in minor burns, can get all the way to fatal burns. It can also cause the muscles of the vital organs, such as the heart, to malfunction. And the degree of damage to a person is based on the magnitude of the current, the length of the time where that current acts, the part of the body touching the live wire, and the part of the body in which the current exists. So, different currents affect us in different ways. 5 milliamps or less, you can get a sensation of shock, but generally little or no damage. In fact, 5 milliamps or less sometimes is being used, say, as a trainer or someone to put a potential difference across a muscle and cause it to twitch. Can be used for therapy and different things. At 10 milliamps, the muscles will really contract. And if you grab a hold of a live wire at 10 milliamps, you may not be able to force your muscles to let go. And 100 milliamps, if passing through the body for 1 second or even less, can be fatal. It essentially paralyzes the respiratory muscles, and you won't be able to breathe, or your heart can stop. So be very careful around different currents. In some cases, currents of 1 amp can produce serious burns, and they can be fatal. No contact with live wires is considered safe whenever the voltage is greater than 24 volts. Now, a lot of electrical devices have a ground wire, and it's really important that we remember to use in the lab devices that always have a ground wire. That third wire, often green wire, if you look at it, is called the ground. And the safety ground is there so that no current, so that there's a path of very small resistance for the current to escape through if something happens. So, for example, here I have someone that's using an electric drill. And I have 120 volts, the hot circuit's coming through the wall outlet into the motor. Now, something happens in the motor, and usually the current is going to flow back along the neutral out to ground. But something in the hot touches, say, the metal on the inside of the drill. The path of least resistance in this case might be right through your body down into the ground that you're kneeling on, and you can get shocked. Whereas in this case, the ground wire, that third ground wire, is hooked up to the body casing of the motor, and if there's a short circuit on the inside, then that ground wire will always have less resistance than your body, and all that will escape down the ground wire. The circuit breaker will detect that there's this sudden increase in current. Well, typically it will shut off, keeping you safe. So if the live wire is accidentally shorted to the casing, most of the current takes the low resistance path through the appliance to the ground. If it's not properly grounded, anyone in contact with that appliance could be shocked because the body produces a low resistance path to the ground. Now, sometimes around your house you see an outlet that's got a little test reset button. It's called a GFI, or ground fault interrupt. And it's used in especially hazardous areas, for example in garages or in bathrooms. It's really designed to keep people from getting electrical shock. And it senses anytime there's 5 milliamps or greater current that is not returning down the neutral wire, so it's leaking somehow to ground, either through a person or through the ground wire. And it's going to shut off that current whenever the current gets above 5 milliamps. So let's review what we talked about today. We talked about RC circuits and how they work. We said for a circuit charging, Q increases exponentially and the current decreases exponentially. Then of course we just talked about electrical safety and some electrical devices that you should know.